Back here with our second video for Chapter 9, Thermochemistry. This is 9.2 Calorimetry. Listed here, as always, are the learning objectives for this section, so please pause the video and copy these in your notes. As promised from the first video in this chapter, Energy Basics, we're now going to really get into calculating this idea of heat flow. Remember, a couple key concepts here. Heat's neither created nor destroyed, so it flows from warmer object to cooler object. And then we know how we're going to calculate heat using specific heat, mass, and change in temperature. So this calculation is called calorimetry. And we're going to use this to measure the amount of heat transferred from one substance to the other. Now, key concepts here is this idea of system versus surroundings. So when we talk about heat flow, when we talk about a reaction or a process being exothermic, meaning it releases or produces heat. So that means that the system is going to lose heat. And where does it lose heat to? It's going to lose heat to the surroundings. Okay, so be comfortable with these two terms. You're going to hear them a lot, system versus surroundings. So in an exothermic situation, the system is losing or releasing heat to the surroundings. And in an endothermic situation, it would be exactly the opposite. The system would be absorbing heat. Where does it absorb it from? The surroundings. Okay, so this is a look at a very basic, what would be referred to as a coffee cup calorimeter. This would be something that that we could set up pretty easily in a general chemistry lab. We use styrofoam cups to help with insulation, right? Because when we have our system in here, so say we have a reaction, often a reaction in solution represents our system. So when we have our reaction in here in this solution, it's going to be releasing heat to the surroundings, the water or the solution being the surroundings, and we're going to see this temperature change. We would love to not have heat also escaping into the larger environment outside of the calorimeter. Clearly, a coffee cup calorimeter that we would use in the Gen Chem lab wouldn't be great at this, although we do get some pretty good results. But calorimeters can be much more efficient at making sure that no additional heat is lost to the surroundings outside of the calorimeter. In the textbook and on the PowerPoint, you'll see some different types of calorimeters that become much more efficient, much more expensive, bomb calorimeters and such. So be sure to take a look at those as you go through your reading. As we get into some calculations here, a couple key points that we want to always keep in mind, right? So first, heat is neither created nor destroyed. So the heat of my system is going to equal the heat of my surroundings, the difference being something's losing heat and something's gaining heat. So we'll make one of these values negative. Okay, so it's the same quantity of heat, but if Q of the system was positive, that means it would be endothermic. That means it would be absorbing heat. Well, that heat would be coming from the surroundings, so the surroundings would be exothermic, would be losing heat. Okay, so keep that basis in mind. We'll apply it differently in a couple different examples here in a minute. The other thing is, of course, how we calculate heat, which was this formula here, this equation here. Okay, so you'll see when we do a calorimetry experiment that often I'll have enough information for one of these two concepts to calculate the heat. And then once I have the heat, I know that for the other, and that'll allow me to calculate how much of it I had or what the specific heat was or the final temperature, things like that. Let's look at an example here so you can get a sense of what I'm talking about. Take a second to read this example problem. So what is happening here is we are heating a piece of metal, a steel rod. We're then taking that heated metal and we're putting it in water. And so what's going to happen is the temperature of the metal is going to come down and the temperature of the water is going to go up until that temperature stops moving. We've reached that thermal equilibrium. I can then use the relationships I outlined a second ago to ultimately answer this question, which is calculate the initial temperature of the piece of rebar. That's what I'm trying to do initially, or to answer this question. So here's how this is going to work. There's enough information here for me to calculate the heat the water gained. The heat the water gained. Okay. We know our relationship is equal and opposite. So the heat of the water is going to be equal and opposite to the heat of the rebar. So the rebar is going to be losing heat to the water is going to be gaining heat. All right. So as I take a look here and I can plug in my values, I can see that I have 425 milliliters of water. Since the density of water is 1.0, that means I have 425 grams of water. We remember this, the specific heat for water is 4.184 joules per grams degrees Celsius. And the temperature change of my water, I can see here that is dropped into 425 mils of water at 24 degrees Celsius. So that's my T initial of water. The final temperature of the water was measured. There's my T final of my water. So I can subtract those two and get my change in temperature of the water. My change in temperature of the water here would be 18.7 degrees Celsius. Okay, this allows me to calculate the heat for my water. Why don't you take a second and solve that? Hopefully you found that our heat of our water is, with sig figs, 33,300 joules. Okay, so if the water gained 33,300 joules, that means I can now set up this calculation for my rebar, and that's going to equal the mass of my rebar, the specific heat of my rebar, and the temperature change of my rebar. So here's where this important concept comes in for calorimetry problems. Since I just calculated this value for the water, then I can plug that right in here while changing the sign to get my heat for my rebar. Okay, they gave me the mass in the problem. They told me to look up the specific heat for rebar and to use it the same as the specific heat for iron from table 9.1. So when you look that up, you'll get. Okay, so now we can do this and we can solve for our change in temperature. Again, so why don't you pause the video and work that out real quick. So when you solved here for delta T for the rebar, you should have received a value of 206 degrees Celsius. So now, ultimately, the question was calculate the initial temperature. So we know delta T equals T final minus T initial. We know our delta T here is 206. Our final temperature, 42.7. Okay, here's another key concept when doing calorimetry problems. The final temperature in both situations is the same value. Okay, so the final temperature for the rebar is 42.7, and the delta T for the water that we got here was 42.7 minus 24.0. So the T final in both situations here is going to be the same value. So that's a really important piece to not miss because remember, when the warmer object and the colder object come in contact, heat flows from warmer to colder until we reach thermal equilibrium in which the temperature doesn't change. So that's another key component here of a calorimetry problem. Anyway, back to our problem here. This would mean that our initial temperature would equal 206 plus the 42.7, or approximately 249 degrees Celsius. This concept is a very common calorimetry type of problem. It's also helpful in identifying unknown metals, where I would have my temperature change and my masses pretty easily, but let's say maybe I didn't know this value. And specific heat capacity is a property that I could then look up. If I were to solve for C, I could then look that value up and identify an unknown metal. So very common process here of a calorimetry experiment. I can also do something similar with a chemical reaction. So pause your video here for a second to take a minute to read through this problem. So the equality I have here is my heat of my reaction, this reaction between the hydrochloric acid and the sodium hydroxide is going to be equal and opposite to the solution that's made after these two things mix. Okay, so I said that often, a lot of times, the surroundings that we're talking about when I think about system and surroundings are a solution that's made in a chemical reaction. Okay, so I have enough information in this problem to solve for my solution. Okay, so mass and delta T. Okay, so the mass one, so a couple things I have to think through here. Okay, so the mass of my solution is after I've added my 50 mils of both aqueous solutions. So I actually have 100 mils, and because it's a solution, all right, AQ, that means it's based in water, right? So a couple things here. That means that my mass here is 100 grams, the 50 plus 50, and because it's a solution, that means water, then I'm going to use that 4.184 value for my specific heat. Okay. Finally, we see a temperature change here is going to be 28.9 minus 22.0, or delta T of 6.9 degrees Celsius. Okay, I can solve this, and I get 2.9 times 10 to the third joules for the solution. Okay, again, back to our concept of law of conservation of energy, heat's neither created nor destroyed. So that means if my solution gained that amount of heat, then my reaction lost 2.9 times 10 to the third joules. Okay, since the Q value is negative, this tells me this is an exothermic reaction, or another way to say it is the reaction produces basically 2.9 kilojoules of heat. Okay, so there you see a couple different ways I can apply this concept of calorimetry. A couple key points here that we always have to make sure we remember is this conservation of energy. So whether I apply it in a chemical reaction in this way, or as I did here with my metal and water, and then I can solve for my heat of one aspect of that and then just transfer that value to the other to help me solve for some unknown. In this case, it was the initial temperature. It could have been the mass of the metal. It could have been the specific heat of the metal. I could have applied that in any way. The other key concept that students often miss was this piece that the final temperature is going to be the same. Okay, so we reach that thermal equilibrium. Something is coming down to that temperature. Something is going up to that temperature. And then we reach that thermal equilibrium. So my final temperature would be the same. That wraps up this section on calorimetry. We will move on to chapter 9, 9.3 in the next video.